complex conjugate of this. So here you have only I alone, the numerator we have only I alone this side, there is no I here, so this alone will change into plus I, so this alone will change to plus I. Okay, multiply this and this. Okay, it is up over there, e power I is here, and of course we have written e power plus I, but in the numerator, in the denominator we have only this side alone, minus I. So we have changed. Okay, now we are going to multiply f by a, its own complex conjugate, so f by a star, so which is equal to, you multiply that, give you this term and this term, correct? So this is f by a, this is f by a, the complex conjugate of f by a whole star. Is it okay? So you multiply, you are going to multiply these two. So when you are going to multiply these two, that will give you I have written 2k1 k2 cos k2 here, I have written this term here, I have changed, I have written here. Okay, I have changed the term and written, and of course we know that this is a minus ib multiplied by this is a plus ib, so the answer is a squared plus b squared. A squared minus b squared will be a plus b, a minus b. Okay, but here it is given as a minus ib multiplied by a plus ib, so that will give you a plus b squared. Okay, so you can simplify the denominator, that will be the answer as a squared plus b squared. Okay, so this is your a, this is your minus ib, this is your a, this is plus ib, so that will give you a squared plus b squared. So you have a squared plus b squared. Cos squared can be written as 1 minus sin squared. So we have simplified like this. So this term, now you just multiply this one and this one. In the next one, we have multiplied these two terms, correct? So we have multiplied these two terms, and we have separately we have written. Separately we have written. That we will have to use a squared plus b squared whole squared formula, a plus b whole squared formula. So a squared plus b squared whole squared formula, we will have to write a to the power 4 plus b to the power 4 plus 2a squared b squared. That formula we will have to write. And second term and the last term will get cancelled. Remaining terms 4k1 square, k2 square, and this third term here and fourth term is here, and just to not cancel, this one will have minus 2k1 square, k2 square, sin square, k2. Okay, you just subtract this two, that will give you this last term. So again we can simplify. So we can denominator as like this. You have 4k1 square, k2 square, of course. So these three terms can be simplified as a squared minus b squared whole squared formula. Okay, we can simplify. Is it okay? You have a to the power 4 plus b to the power 4 minus 2a squared b squared. You have to use that formula and get the final expression. So this is the final expression. And your transmission coefficient is defined as transmitter flux divided by incident flux. Actual definition for your transmission coefficient is given by f star f v1. v1 is the velocity of the particle in the first region. So a star a first region. So this is the actual definition. So v1 will get cancelled. You have this expression. So this is the final expression, and this expression stands for the transmission coefficient, which is a very, very important expression. Okay, this can be simplified again. This can be simplified again, dividing by this denominator factor. So that will give you 1 divided by 1 plus, see, 1 divided by 1, this one will go off. You have 1 divided by 1 plus k1 square minus k2 whole square, this term into sin squared k2 here. Okay, so this is the final expression for the transmission coefficient, equation 2.97. This equation can be simplified in terms of now electron volt, in terms of E and V naught, because of course K is connected with the energy. Okay, we know already K is connected with the energy. So this can be converted into in terms of electron volts. Okay, it can be converted into potential. This is potential and this is energy. How it is possible? This is K1 squared equal to 2mE by h bar squared, we know already. K2 squared is given by this one. We need to have K1 squared minus K2 squared. So you just subtract that, will give you E will get cancelled. You are going to minus this one. Okay. So this will become plus. So this answer you will get this answer. So squaring on both sides will give you 4m squared divided by h bar to the power 4 V naught squared. So we have found out the expression. You multiply these two. This multiply these two. That will give you k1 squared, k2 squared is this expression. You will get k1 squared, k2 squared equal to this term. You substitute here. So instead of k1 squared minus k2 squared whole squared, that will give you 4m squared by h bar squared. Correct. So this term and this term will go off. You have v0 squared divided by this 4 is here, e minus e multiplied by e minus v0. Is it okay? These two terms are same. You just cancel this one. You will have v0 squared divided by 4e e minus v0 sin squared k2l. Your transmission coefficient depends on e, depends on v0, depends on l. It's a very important one. Okay, depends on l. So if the thickness of the barrier is very small, easily it can transmit. So that's why I said it's very important that T depends on L. We can show that the transmission coefficient unity whenever this term goes with 0. Suppose if it is 0, we can analyze. See, if it is equal to 0, we can say that 1 plus 0, 1 divided by 1, that will give you 1. So transmission coefficient is equal to 1. Not only for this term goes to 0 means K2L equals n pi for all the terms, for n pi. Okay, for pi, for 2 pi, for 3 pi, for every term this will become 0. It will approach only transmission coefficient, which is T equals 1. It means that we can have a constructive interference when K2L equals n pi, if it undergoes this condition. For constructive interference, we know that K2L equals n pi. Okay, so this condition is equivalent to L equals n pi by K2, and of course we know that K2 equals this expression. So we have K equals 2 pi by lambda. Okay, so K2 equals 2 pi by lambda 2. So n pi lambda 2 by 2 pi, we have n lambda 2 by 2. We have the perfect transmission. This term goes to 0. So fully transmission coefficient is 1. So if its transmission coefficient is 1 means perfect transmission. So that will go only with this condition is satisfied with K2L equals n pi. So this is what constructive interference goes. So, and of course lambda 2, it falls in the second region. Okay, so that's why we written as lambda 2 equal to h divided by p2. It's a wavelength in this region. So this is the graph, transmission coefficient for the potential barrier. So look at the graph, the transmission squared with E divided by V0. E by V0 is very important quantity. Okay, E by V0. And here, this is what I said. Here we have for K2 equals n pi, for all the constructive interference, it will approach to transmission coefficient. See, it approaches 1. It approaches 1 here. It approaches 1 here. So it occurs the perfect transmission. So where it touches, it's called a perfect transmission because T equals 1. That is a maximum value. T equals 1 is a maximum value. So 1 means perfect transmission. This curve, we have drawn this curve, T versus E by V0, E by V0. You will get this graph. And this curve touches exactly at this point. See, this point and this point and this point. So it means that it should satisfy this condition, lambda by 2. N lambda by 2. See, this is first lambda by 2. This is second lambda by 2. This is third lambda by 2. So where we can have a constructive interference, where it touches the maximum value. So here we have a perfect transmission, constructive interference. Here we have a perfect transmission, constructive interference. For the next constructive transmission will be here this point. Okay. So for perfect transmission we have K2L equals n pi. So squaring on both sides, that will give you K2 squared L squared equal to n squared pi squared, and K2 squared equals, we can write this as, we know already K2 squared equals 2m by h bar squared E minus V0. So substitute in this expression, you have 2m by h bar squared E minus V0, L squared equals n squared pi squared. You bring all the term that side, so you will have E minus V0, which is equal to, you bring all the term, 2m by h bar squared L squared to right hand side. You will have E minus V0. You bring that V0 to that side. You will have E equals V0 plus all those terms. Is it clear what I am saying? So you bring h bar squared to this side. So you will have h bar squared n squared pi squared divided by 2m. This L squared also. So you will have 2m L squared. See, 2m L squared. N squared pi squared h bar squared. Left hand side you will have only E minus B naught. You now bring V naught to that side. So you will have E equals V naught, this term. Now look at the expression. This is for the infinite square potential. The expression for the infinite square potential. When H tends to 0, suppose if H tends to 0, so you will have E equals V naught. This is the classical result. When H tends to 0, this is correspondence principle, Bohr's correspondence principle. We have already discussed this one. When H tends to 0, when lambda tends to 0, for a large number of n, quantum results will go into classical results. It will show the classical results. See, now look at this one. H tends to 0, you have E equals V naught. E equals V naught is the classical result. Okay, when E equals V naught, we will have perfect transmission. There will be no reflection at all. So it obeys exactly the classical results also. Okay, so now we will see. Thus we can say that whenever the barrier region contains an integral number of formulas n lambda by 2, okay, we will have a complete transmission. We will have a complete transmission n lambda by 2. The second one, as I said, we will have a constructive interference, okay, where it touches the transmission curve. So this is what about the maximum of the transmission coefficient coincides with the energy eigenvalues of the infinite square wave potential. These are known as resonance. So they are called as resonance. This resonance phenomena occurs from a constructive interference between the incident and reflected wave. So this phenomena is called Ramsar-Townsend effect, which describes the scattering of low energy electrons from noble gas atoms. Okay. So according to the equation 2.98, so this is equation 2.98, the transmission coefficient is an oscillating function. But of course, sine curve is an oscillating function. So it goes to the constructive, destructive, constructive, so it's an oscillating function. So finally, when E is greater than V naught, the transmission coefficient ultimately becomes 1. Ultimately becomes 1. Okay. Thus T is finite. Of course, T is finite. This means that probability for transmission of the particles into the region X is greater than L is not 0, as in classical physics. However, the particle can in no way make it to the region X greater than 0 in this region. So this is purely quantum mechanical effect, which is due to the wave aspect of microscopic objects. All microscopic objects will tunnel through the barrier. So this is what is given, unlike in classical physics. Even though the kinetic energy is less than that of potential energy. So that's the idea. If kinetic energy is less, classically it cannot go into the barrier, it cannot cross into the barrier classically. Whereas in quantum mechanics, if kinetic energy is less than, for the quantum particle, less than the potential energy, it can cross, provided the barrier should be very, very thin. So this is purely quantum mechanical effect, which is due to the wave aspect of the microscopic object. So this is known as tunneling effect, penetration. So quantum mechanical objects can tunnel through the classical impenetrable barriers. This barrier penetration effect has important applications in various branches of modern physics, ranging from particle to nuclear physics. For nuclear physics, this is what alpha decay we discussed right from the beginning. To semiconductor devices, tunnel diodes, STM, tunnel diodes, decay. So these are the examples we can give for the tunneling effect. So radioactive decays, okay, that is nucleus will turn into another nucleus, new nucleus. Okay, radioactive decays and charge transport in electron devices, charge transport devices, tunnel diodes are the typical examples for the tunneling effect. So similarly, we can get the expression for reflection coefficient also. We have got the transmission coefficient. Similarly, we can get the reflection coefficient R, which is equal to B by A multiplied by its own complex conjugate. We will get the expression. Okay. So you can just write down the expression. We need not solve. Okay. And so that from equation, this equation and that earlier equation for T, we can get R plus T, which is equal to 1. So this condition also can be satisfied if E equals greater than V naught. If D is greater than V naught, there will be no reflection. T alone will exist classically. Right? So T equals 1, R equals 0. There will be no total transmission for high energies and weak potentials. Now for the second case, where E is less than V naught. E is less than V naught, immediately we can get K2. This term will be negative 1. And of course, we need to have only psi will be a positive 1. Okay, psi should be real. we need to have. So in this condition also, we can also get the same thing, provided this when E is less than V naught, the momentum velocity within the region is imaginary, because this is negative. So you will get only imaginary value. We will have the same expression for psi 1, we will have the same expression for psi, okay, in the first region. Second region also we will have the same region except I will not be there. Third region we will have the same expression. So this is all the differential between E less than V naught and E greater than V naught. In E greater than V naught, in all the expressions for wave function, we will have E power I. Okay, E power I term. But E less than V naught, at the center region, at the second region, this will be E power I, not I, it E power simply K1x. Sorry, K2x. This is in the second region. So E power K2x. There it is E power I K2x. Here it is E power simply K2x. So that's the difference. Now, this typical diagram that shows that we have large number of quantum particles. After penetration, see, you will have less number of particles, 10 to the power 10. So suppose it is 10 power 18 particles that are going. Of course, it depends on the size of the penetrating barrier. Okay, it depends. Okay, this is a typical example we can say. 10 power 18, that will give you 10 power 10. Okay, 10 particles. So for E less than V naught, we will have the same expression except there it is sine, here it is hyperbolic function, sine h. So that's a difference. Okay, suppose we want to simplify, this will have a lengthier derivation, so which is out of your syllabus for you. You will have to solve either one, either E greater than V naught or E less than V naught. Simply you can write the expression for the examination purpose. Okay, so here it is hyperbolic function. Okay, there it is simply sine squared, it is sine h squared. Of course, the terms are equal, terms are the same. So you have T equals this expression. If you substitute K2 squared equal to 2m by h bar squared V naught minus E, because V naught is greater, correct? V naught minus E, you substitute and you will get the expression exactly like this. Okay, now what I am going to do is, I am going to pull this V naught out. So that will give you E V naught 1 minus E by V naught. So V naught out, that will give you V naught 1 minus E by V naught. E by V naught I can keep it as epsilon. So this will become epsilon and this will become epsilon. This V naught square and V naught will get cancelled. This V naught I am going to bring it to down, that will be E by V naught. Okay, is it okay? This V naught squared, V naught will get cancelled. This V naught I am going to bring it to here in the denominator E by V naught. E by V naught is nothing but epsilon. So this becomes epsilon. So epsilon 1 minus epsilon. Right. So you have 4 epsilon 1 minus epsilon. So sine h bar square. This term is termed as with L. So lambda. So that will give you sine h square lambda 1 minus epsilon. So all these terms can be brought to the numerator, that will give you to the power minus 1. Is it okay? Transmission coefficient. So I have written the same thing. For this condition, E is less than V naught and your epsilon will be very, very less. Okay, you just E is less than V naught, your epsilon will be very, very less. Okay, and your lambda, that term will be always greater than 1, just opposite nature. So lambda, because your V naught is greater, so lambda must be greater, V naught is greater, lambda must be greater. So you have lambda root of 1 minus epsilon will be greater than 1. So using this condition, this expression can be simplified as 1 by 2 e power lambda to the power 1 minus epsilon naught, and the complete transmission coefficient can be asymptotically for the larger distance that will be given as exactly this expression. Okay, your transmission coefficient is given by this expression. Okay, this is to the power minus 1, 2 to the power minus 1, so that will be minus 2. So e power minus 2 lambda to the power 1 minus epsilon. This minus 1 I can bring into the numerator, that will give you, this is squared, okay, this is squared. So 4 multiplied by 4, that will give you 16. So 16 epsilon 1 minus epsilon. I repeat, see here this is squared is there, here minus 1 is there, so e power minus 2 lambda, that term. So here 1 by 2 squared is there, so that will give you 4 4s are 16, so 16 to the power minus 1 to the power minus 1, so that will give you 16 epsilon 1 minus epsilon and this term. Is it okay? Now I can substitute for epsilon equal to E by V naught everywhere. So this is your complete expression when E is less than V naught in the next condition. Okay, is it okay? Any doubt? So E is less than V naught, this is the expression. Okay. Now we'll solve two problems. So which are very important problem. Problem number 1. Using this this one. Okay, this expression. 1 electron got trapped inside the surface of a metal. If the potential barrier is 4 electron volt, so your barrier height is 4 electron volt, and the width of the barrier is 2 angstrom. So width of the barrier is 2 angstrom. Calculate the probability of its transmission. So we are going to find out the transmission coefficient. So it should be less than 1. Okay, if it is 1, it is classical. It should be less than 1. Or it will be in terms of percentage. Okay, so this is what the idea is. Now what is given here? Your E will be 1 electron volt. So this must be 1.6 10 to the power minus 19 electron volt. Your barrier height will be V naught equals 4 into 1.6 10 to the power minus 19 electron volt. Okay, so your L will be 2 into 10 to the power minus 10 meters. What is the formula that we are going to use? T equals 16 E divided by V naught, 1 minus E by V naught, and the exponential this term. You substitute. So you have 16. E by V naught is 1 by 4, correct? 1 minus E by V naught, 1 minus 1 by 4 will give you 3 by 4. 1 minus 1 by 4 will give you 3 by 4. The remaining term E power minus 2L. L is 2 into 10 power minus 10 divided by H bar. H bar equals H divided by 2 pi. H is 6.63 10 power minus 34 divided by 2 pi will give you this term, and remaining term 2 into this is for the electron. So mass of the electron is 9.1 10 power minus 31 kgs, and remaining term will be V naught minus E. V naught minus E is 4 minus 1. So 4 minus 1 is 3. V naught minus E. In terms of electron volt, so it's written as 1.6 10 to the power minus 19. So here I have made a mistake, 1.6 10 to the power minus 19 joules. Okay. This in terms of electron volt, correct? So it must be joules, 1.6 10 to the power minus 19. Okay. Now you just simplify. So you will get T equals 0.085. So it means 8.5%. Okay. It depends on, mainly depends on the barrier width. Okay. The barrier width is very, very, very small. The transmission coefficient will be very, very high. Okay. So T will be 0.085. So 8.5%. Now we'll go for the second part. So an alpha particle is trapped into the nucleus of radius. So this is for the alpha decay, and this is for the ordinary penetration problem. So I have separated these two. Okay. So that's for the potential barrier, and this is for the alpha decay. Okay. So this alpha decay problem arose in the year 1927, immediately after Schrödinger found out the equations 1926. So after 1927, so these problems, alpha decay, alpha emission, which you are going to see later, so those problems arise in the year 1927, by gamma. So an alpha particle is trapped in a nucleus of radius 1.4 in 10 power minus 15 meter. What is the probability that it will escape from the nucleus if its energy is 2 mega electron volt? So this is mega electron volt. Mega electron is 10 power 6 electron volt. The potential barriers at the surface of the nucleus is 4 MeV, and the mass of the alpha particle is given by 6.64 into 10 power minus 27 kg. Now energy will be 2 electron volt. So this must be 2 mega electron volt. So this must be 2 into 10 power 6 into 1.6 10 power minus 19, and V naught will be 4 MeV. So 4 10 power 6 multiplied by 1.6 10 power minus 19. Okay, and your R will be, radius is given as 1.4 10 power minus 15. So it is not electron volt, as I said, it is joules. Okay, it is joules. Okay, don't forget. So the formula is given as T equals 16 E by V naught, 1 minus E by V naught, and E power. So 16, I have written 16 E by V naught. What is E? E is 2. V naught will be 4. So 2 by 4. So that will be 1 by 2. 1 minus E by V naught. 1 minus 1 by 2. So that will be 1 by 2. And the exponential minus 2 into, your R is given as 1.4 10 power minus 15. And you will have to calculate the 2 times diameter. 2 times the radius. So that will give you L equals 2R. So 2 times 2 into this 2.8, okay, 2 into 1.4. So 2.8 10 power minus 15. This is usually the range of the nucleus will be 10 power minus 15. For the atom will be 10 power minus 10. Okay, so 2.8 10 power minus 15 divided by your H bar, the value for H bar is given as this one. 2 M will be 1.64 10 power minus 27 multiplied by V naught minus E. V naught minus E will be 4 minus 2, that will give you this. Okay, 2 into 10 power 6 mega electron volt multiplied by 1.6 10 power minus 19 joules. So your T is 0.124, just 12.4 percentage. Okay, there the answer is 8.5%. Here it is 2.4%. The transmission coefficient will be very less. It will not be more than. It will be more than this will approach classical physics. So few electrons will penetrate. As we discussed, 10 power 18 means this side you will get only 10 power 10. Okay, not 10 power 17, 10 power 16, which is enormous. We will get the value. Okay, 10 power 18 means 10 power 10 it will be. Okay, so that is the end of potential barrier, and this problem is very, very important because we are studying the quantum tunneling effect only in this problem. Okay, nowhere else it occurs. Okay, thank you students. We will stop.